Hello everyone, my name is Chinmay Gaur. Hello everyone, I'm Chinmay Gaur, co-founder Equim Architecture and Equim Education. And let me go ahead and share my screen so that I can have a word with you guys and also know how the audience is doing today. So, so Equim is an architectural and research organization, and we have been working in the field of renovating, kind of innovating in the field of architecture, wherein we fuse parametric architecture with vernacular architecture and locally available materials and locally available techniques in India. And we st we have two verticals. One of them deals with architectural planning and designing services, where the other one, Equim Education, deals with educating the architects and students of India towards the field of parametric architecture. So, let me just quickly have a word with the people in the chat box. So, guys, I would like to know how many of you are actually beginners and how many of you are actually have been using these tools. So, type yes if uh, you are a complete beginner, you have never used tools of parametric architecture before, or type no if you are if you know something about it, so that we can adjust the pace of today's session as per that. And people watching us in on YouTube, you guys can also start typing in the chat box. So keep this session. Okay, I see most of them are saying yes, a couple of no's. Okay, that's great to see that some of the people have some sort of knowledge towards this domain. Okay, great. Um, some people are saying that my voice is echoing, so if someone can give me a confirmation if I'm sounding fine. So people on YouTube and on Google Meet as well. Okay, great. So let's begin our today's session. I see most of you are beginners here, so we'll proceed with that phase itself, with that pace itself, and we might also have in the end, towards the end, we might also have some advanced topics to cover, some advanced topics as well. So let's first of all try to understand what is parametric architecture and what is the first all about. So I'm sure you, most of you must have seen these complex buildings. The first one is iconic building by Zaha Hadid in Baku, and then there is Guggenheim Museum and the building in the center. So I'm sure you all must have seen these buildings throughout your architectural education, and if you guys are practicing, then too. And sooner or later, we start relating these complex forms to parametric architecture. But is just the mere form of this building parametric architecture? Is this complex form parametric architecture? These twisting buildings and these circular complex looking buildings are, is this what parametric architecture is, or is this computational design? So before we begin with our session today, let's understand that it is a myth that complex looking building is parametric architecture. It is a myth that the computer or the software automatically generates the design for us and we just have to sit back and relax. It's a very complex process, and it involves a lot of to and fro between the architect, the designer, and the computer. And no, the computer not does not automatically generate the designs. Parametric architecture is all about optimization. And yes, these complex buildings, these complex facades are one of the outcomes of parametric architecture. So with that particular mindset, let's move forward and understand why parametric architecture is important, why it is the need of the hour, and how we can start implementing. So this workshop, this particular webinar session has been divided into three modules. So firstly, we'll try to understand through this presentation what is parametric architecture, and toward in the middle we'll look into some practical aspects, and then in the last we'll see what is the scope of parametric architecture. So that is how we're going to go forward. So let's begin by understanding a little bit of history here. So if I talk about evolution of architecture versus other fields, so if I talk about evolution of architecture versus other fields, so you see, we as human beings began to find shelter. The architecture is as old as human beings. We started finding shelters by putting up these rocks so that it could protect us from harsh rain or harsh sunlight and things like that. Then we moved on to living in houses. We started putting up walls because we needed some privacy. Then we started living in neighborhoods because we are social human beings. And once we started living in neighborhoods, the land wasn't enough, so we started rising in height. So we started building stories over stories. And that's how high-rise building, low-rise, and high-rise building came into existence. And there were many type of styles that I don't want to get in details here, like uh, minimalism, brutalism, and Le Corbusian style. So there have been many sort of styles that I'm sure you all must have studied in your history classes in architecture. So let's not get into those. Let's see what stage we are at right now. So we have moved from so many uh, phases of architecture. We got to minimalism, and then now we are at complex geometries, and we have skyscrapers. But the question is, are our buildings smart? So let's answer that question by looking at the evolution of some other fields. So if I talk about automobile industry, we began from a simple stone wheel. It was tied to a pulling cart, and it was a pulling cart that a human pulled. Then it was that pulling cart was tied to an oxen or to a horse, and there was or to a bullock. So there was a bullock cart, and that's how we started with transportation. And gradually we started building engines, and we tied a motor engine to that cart, and we had our first motor car, right? But did we stop there? Did we stop there at motor car? No, because as we move forward in evolution, things improve over time. So we started innovating in automobile industry, and now we are at a stage where companies like Tesla, like Ford, they have been innovating, and we have autonomous vehicles now. We have self-driving cars. We have cars that have AI integrated within them. They can come in a sense, they are now a living being. They can communicate with their surroundings. They can communicate with people around them, obstacles around them. They can communicate with other vehicles. They can connect to the internet. So in a sense, they are some sort of organism now. They are no more a non-living thing. They are somewhere between non-living and living. Right. So that is how automobile industry has evolved. And if I take a moment here and think about your smartphone. We moved from telephones to smartphones. Think about refrigerators. We have smart refrigerators. We have smart bulbs, smart lights, smart ACs. That is, everything is connected to the internet. They are constantly uploading the data, syncing with other devices, syncing with our phone, communicating with us throughout the day. So that is how all these fields have evolved. So if I talk about evolution of computers itself, so we began with a very basic abacus here, in which we moved these beads up and down to perform basic mathematical calculations like addition, subtraction, division. And gradually we moved on to computers. If you remember from 90s, I don't know how many of you are from 90s here. So in early 2000s, we had computers that had huge CRT monitors and huge desktop systems that had RAM of about probably 15 MB, 20 MB, 50 MB, and a hard disk capacity of 1 GB, sometimes 256 GBs. That's how we progressed. And now we're living in a phase where mobile phone that fits in our hand has over 6 GB of RAM and probably 128 gigs of storage. And we also have supercomputers and quantum computers that can perform calculations. So this is an important term, that can perform calculations that are incomprehensible to human brain. We cannot even make sense out of it, that they perform in the matter of seconds. So that's how computers and computational energy has evolved. If I talk about evolution of construction being architects, so I would also like to know, is everyone in the chat, is everyone here in the audience an architect or an architectural student, or do we have people from some other field as well, maybe from some other designing fields? So go ahead and drop in the chat, drop in the chat box. What do you do? So okay, so if I talk about evolution of construction, so we started from assembling rocks, and then we used chisels to carve out structures in the caves. We lived in the caves. Then we moved on to, I don't want to get into the details of all the types of construction here again, because I want this conversation to be future oriented. So we moved on to stone masonry and brick masonry and mud mortar, cement mortar, concrete structures, shell structures, and all. After all these things, we came on to prefabricated systems. Now, prefabricated system was a new thing in countries like USA and China and all these developed countries 20 years ago. Prefabricated system. It is a very old thing now. In India, it is no more a very new thing, but it is only seen in practice in tier 1 and tier 2 cities, and that too majorly in tier 1. So we are still lagging behind on prefabricated system. The new thing in USA and China and all these developed countries is CNC cutting, CNC milling, 3D printing. So the researches are going on. So the image that you see on the right here, this particular image where a robotic KUKA arm is basically printing this concrete vast sort of structure. It's no more a hypothesis or a conceptual render. It's a reality, and we have moved on to a phase where we can directly 3D print mud, and we can directly 3D print concrete and different types of things. And constant researches are going on to scale this process. IIT Chennai has developed a working prototype in which they can directly 3D print units of size of a kiosk of a room. So it's just a matter of time. Let's say 5 years down the line, maximum 10 years down the line, we'll be at a stage where we can directly 3D print houses or maybe small rooms, and eventually even the entire neighborhood or the buildings or the entire city. So that is where construction industry is headed with this space. Let's see how evolution of technology happened. So I don't want to get into the technicalities again of this particular graph here. So what it suggests is this is a basic Moore's law, uh, which was devised in 1980s, and all it tells is the computational power basically doubles every 2 years. So if in 1 square millimeter, earlier you could fit 10 transistors, if in 2020 you can fit 10 transistors, then in 2022 you'll be able to fit 20 transistors in the same 1 square millimeter of the area. So that means in the same space we can increase or double the computational power. So that is what this graph suggests here. And to put it in a generalized terms, not getting into the technicalities, think about how softwares and apps come out. Think about how they are evolving. So by the time I'll finish this particular webinar session, there will be multiple new apps and softwares that have been already been pushed out into the market to be tested by the users. So that is the pace of technology we are living in right now. And now, after everything, let's talk about evolution of architects. So if I talk about evolution of architects, we start the image that you see on the left. We started from hand drafting. So imagine when the Red Fort was being built, whoever the architects were, they did not design it on a computer. They had huge sheets of paper laid down. 15 of them would climb onto one single sheet of paper and they would draft. And I'm just using Red Fort as an example. There are multiple buildings that existed before AutoCAD that were constructed. How were they constructed? How were the drawings made? So multiple architects and draftsmen would climb onto a same sheet, and then they would take a ruler and French curves and make everything manually. That's how architects evolved. Now we have moved to a phase, the image that you see on the right, and I'm sure most of you are aware with the program running on the system here, CAD systems, computer aided drafting. So what this did is it made scale no more a problem. So doesn't matter if you want to design a room or Burj Khalifa. A single person can do that sitting in front of a screen. So scale wasn't a problem. But what was the problem? Earlier, when we had to draw a line, we took a ruler, we took a pencil or pen, and we drew a line manually. Now, when we have to draw a line, we press L enter and draw the line. Has the Yeah, I understand that the medium has changed. I understand that it's faster now. But is the manual labor of architects stopped? Are we using the entire power of this CPU or this computer that it has to offer? No. Are we relying for any decisions on computers? No. So that's where we are lagging behind. When all the other industries are actually relying on computer to make better decisions for them, we are not. And why is this? Why have architects not evolved? Why are we still stuck 20 years in the past? So there comes architect's ego or some challenges. So there is the first thing is comfort zone. So when you are in first second year, when you move to AutoCAD, things become easy. But then when you start trying to migrate to, let's say, Revit or BIM tools, they are slightly complex. They need some extra energy from your end, some extra efforts from your end to learn and start using them in your practice or in your assignments. So we are stuck in a comfort zone. We don't want to put in that those extra efforts to evolve ourselves. And this is the case with students. Let's talk about the architects. So imagine you had a practice for last 10 years and you are getting projects at a constant basis, and you have evolved to a certain workflow. You have a certain workflow set in your office. Then why go through the extra hassle to train all the employees, to spend the extra money to train all of them, and spend the extra time to train all of them with these new updated tools like tools of computation design and parametric architecture? Why? When you are still getting the projects, when you still have the same revenue. So comfort zone, people don't want to come out of the comfort zone. And then we as Indians are a bit slow to adapt to the technology, and I'm sure you would agree with that. Not our generation, but now think when you are trying to explain a new app to your parents, how many times do they ask you the same question? So we as Indians are a bit slow to adapt to the new technology. And there is something called architect's ego towards design, that if every inch of the building is not designed by the architects themselves, it is not a very nice architectural building. So that is something that we need to overcome. Our duty and our responsibility is to make sure that we put whatever buildings or built mass that we design and put out is very responsible, is sustainable, does not increase carbon footprint. That is the biggest responsibility that we have in the current scenario in India, right? So also before I move forward, I would like to ask you guys, take a moment here and imagine how the classrooms have evolved. Imagine the classrooms your parents sat in, and imagine the classrooms we have now. So, our parents sat in a classroom where there was a teacher who taught, and then there were a bunch of students sitting in front of the whiteboard or blackboard, grasping the knowledge or adapting the knowledge. But now let's talk about how we have evolved. Think about your college. Has anything changed apart from the fact that you bring a laptop to your college now? Has anything changed? Has the medium changed? Have we become interactive? Please keep yourself on mute. Um, if anyone is unmuted, please keep yourself on mute, and we'll have a question and answer towards the end of the session. Okay. So classrooms haven't evolved, teaching methodologies haven't evolved, and that is why it is a need of the hour to find some parallel education systems in which there could be some sort of informal learning through which we can learn and adopt and learn these tools and collaborate with one another, because architecture is a multidisciplinary stream. It's not that if you learn architecture, you'll learn everything. You'll have to collaborate with physicists, with structural engineers, with chemists, with multiple horizon of trades before you become a very good architect. So colleges like A London, IAC Barcelona, they have multidisciplinary system in their colleges. That is something that we are lacking. So we need to have a bit more informal education system set up parallel to the existing one. And again, COA is not doing a very great job in regulating how the colleges are upgrading their syllabuses. So education system is kind of outdated. Okay, enough with the pessimistic approach. Let's try to learn what is parametric architecture and why it is important and how we can start using it. So before I dive into that, let's understand what is data. So in 21st century, that is a century of digitalization, that is a century of uh, innovations in technology. Data is the most important thing. Data value has surpassed the value of oil and gasoline. And to give you a idea of how mankind is producing data, one zettabyte is 1 billion terabytes. And in the year 2010, we produced around 4 zettabytes of data, that is 4 billion terabytes annually. By the year 2019, we have already produced around 38 zettabyte of data. And this is not the entire data. This is something that we are producing annually. So we produce 38 zettabytes annually. And uh, with this graph, you can see by the year 2025, we'll be at 175 zettabytes per year. And this data is selfies, videos, every click you make, every website you visit, every online conversation that you have, everything is this data. And this data is very powerful. Corporations like Google and Facebook, they have the power to turn down entire governments, to select presidents. So that is the power of data. And how does that relate to architecture? So if I talk about architectural data, when we are presented with a design challenge or a problem, be it a live project or a college project, what do? We either visit the site, or if the site is hypothetical, we collect some data. What is the data that we collect? The wind movement, the sun movement, where is the north, what is the groundwater availability, how is the soil bearing capacity, what is the site condition, how is the seismic activity, how does the neighboring building looks, how are the neighboring buildings designed, what is the visibility of the site from the road, and multiple other data, right? What is the humidity? And we collect all these data, and we start begin with the design process. And after we have designed, when we move towards constructional phase, we start collecting data of the materials that we are going to use. So how much heat will the material absorb, how much will it give out, how would it perform in terms of environment, what is the carbon footprint, is it locally available, will it be imported from somewhere else? So all this data, this is something that we collect, and this list goes on and on, because architectural projects are very elaborate and you all must know that. So there is a huge list of data that we collect throughout an architectural challenge or a design problem. So if I talk about wind and sun movement, if I talk about humidity, it is a technical data. It is fairly technical. It is scientific data. So wind is we get the velocity and the direction of the wind, we get exact azimuthal numbers of sun, and then there are u values, how per square millimeter or per square meter, how much heat is getting in and getting out, and all these things. These are very technical data. Seismic data is prepared by geologists. So we as architects are not trained to understand that data precisely. Yes, we have an overall understanding. What does it mean to keep the north low, the south high, how to cut out the sun, right? We have a basic understanding of it, but we cannot comprehend that scientific data that we collect. It is a scientific data, right? It has some scientific units. It is a scientific data. So we do not have the knowledge to comprehend this data perfectly, because it's not our field. That's not our job to comprehend this data entirely, right? Because we have to design buildings. We are not geologists. We are not weather experts. So I'll circle back to this slide again. Let's understand what is parametric architecture. So parametric architecture is basically finding the simplest solution to a challenge or a problem with objective evaluation of different data, like the data that we collect throughout the challenge. And it is an objective evaluation. Objective evaluation means to evaluate something keeping the subjectiveness aside, based on formulas and algorithms. So objective evaluation of different data and parameters like wind, sunlight, weather conditions, and all these data that we talked about just now, and coming up with the most optimized result. So this is something really important. So this is what parametric architecture is, to come up with the most optimized solution. So optimization could be in terms of sunlight, could be in terms of wind, could be in terms of costing, could be in terms of material usage. So coming up with the most optimized result is parametric architecture. And computation is generating solutions after processing these data, this particular data, using mathematical algorithms. And once you have done that, then you spot patterns between the data, and then finally you optimize your output based on all the information that you have at hand and connecting the dots. So that is what parametric architecture is. To give you an idea, so okay, to give you all an idea, let's see what is traditional, how have we been practicing so far, and what parametric architecture changes. So traditional workflow, in it we have a design challenge, right? And we collect all the data that we just talked about, and then we as architects, what do? We use our intuition, we use our experience, we use our subjectiveness, and then there is a list of requirements from the client, and then there is some emotionality attached to it, and then there are some psychological factors as well. So intangible data. Basically, we use intangible data to comprehend a very tangible data. These data is very scientific that we collect, right? Then we evaluate based on our understanding. But then the solution that comes out of us is not absolute in nature. It is not absolute. It is neither tested nor optimized. It could be a very good performing building, or it could be a very bad performing building. We would never know until we build it or we simulate it on computer. And if we simulate it, we have to move towards parametric workflow. And then again, the data, as you can see here, the dotted line, the solution that comes out is fragmented because we lost this information here. Once we evaluated all this tangible data using our intangible logics. Now let's see how parametric workflow changes the things. So again, similarly, we collect data. We have a challenge here. We collect the data, and then there is some computational tool that can easily understand this scientific data. And we as architects feed in all our requirements, emotion, psychological attributes, intuition, experience, subjectiveness to that tool. Then it generates a design for us. This design is tested, optimized, and if we are not happy with the design it has generated, we can always go back and tweak the data that we have provided or tweak this data, come up with a new solution and use that. So I'm not saying this would give you a perfect building, 100% optimized building, but what it would give you is a number. It would tell you, let's say it would tell you that your building is 80% optimized towards the sun or solar radiation. Now, as architect, it's in your hand. Now you get to choose. Get to make an informed decision whether you want to proceed with that design or not. So you can either circle back, improvise on the design, or if you choose to go forward, you'll know that it is 80% optimized. There is no trial and there is no guesswork. It is perfect data. It is absolute in nature. Let's have a look at uh, what are some solutions that are generated through traditional workflow. And so if I talk about traditional workflow here, again, I'm not trying to say that this is the only type of building or this is the only type of solution we get through traditional practice. There have been great architects. There are great architects that design great structures that perform very well. What I'm trying to say is this is the most usual type of form that you see across tier 1 and tier 2 cities. So if you talk about Delhi, Bangalore, Noida, Hyderabad, Pune, Mumbai, you'll see you'll mostly see buildings like these. Now, if I talk about sun movement here, so it goes like this. Let's suppose. So do all of these face respond in the exact same manner to the sunlight? The windows in the niches, this particular face here, do they respond in the same manner to the sunlight? No, they don't. Do they respond in the same manner to the wind that comes in? No. But did the architect take in account all these factors? Probably not. So how these structures are made, usually you make a one single floor plan, then you replicate it in height, you get a tor. And then you replicate that tor throughout an array and you get a group housing or a similar structure like that. But this face here responds to the factors differently, the rear face differently, and all these faces, all these structures respond to all these factors in a different way. So did we take that in account? No. And this is horrendous. This is something that we as architects shouldn't be doing anymore. Humanity as a race is heading towards a verge of collapse, and it is in our hands to make sure that whatever we are designing and we are putting out in the world is responsible enough. Let's have a look at parametric workflow solutions. So if I talk about parametric workflow solutions, so this is Al Bahar Tower in Dubai. So this is a kinetic facade basically. So the designers must have had a sun, they simulated it, and they wanted to make a commercial space. So that means they had to use a glass facade all over it. But to cut down the sun, how do they cut down the sun? Either they increase the cost of cooling, artificial cooling, or mechanical cooling, or they do something on the facade that cuts down the sun. So they simulated it and they got to know that these are the faces that would be mostly exposed to the sun. So they designed a fenestration. They designed sort of a brise soleil basically. So these are something like this. So this is basically a hexagonal ring in which there are these flaps that open up or close based on the sunlight. So if the sunlight is direct and harsh, they would open up to prevent the sunlight from coming in. And if it is indirect, it will close to let the indirect illumination to come in. So these are called kinetic facade. And again, I'm not saying the cost of this operating this might be very higher than the cost of mechanical cooling. What I'm trying to say is this is one step forward. one step forward towards the future. So we have to innovate this. We as architects have to take inspiration from it and we have to innovate it further. How we can use something else, how we can make it better, right? That's how we did not have a car did, at just first step. It was a cart, it was a bullock cart, it was a basic motor engine. Then now we are now we have gradually progressed to a phase where we have luxury cars and we have the cars that we see today. So it's an evolutionary process. So try to put yourself in that mindset that you have to evolve. You have to evolve the entire architectural practice. Think like a researcher. So this is a housing solution designed by Zaha Hadid architects, and you see how this high-rise tower is being received by low-rise buildings, kind of enveloping it, and then they have been oriented in a way that are very organic, and these are not some random curves. They have basically been simulated on the computers based on sun and wind, and they regulate the wind flow among themselves. So if wind comes like this, it will circle and go out like this, right? So that's how these structures have been designed. And now imagine if this square here, it does not receive much of the sunlight. So what computer will do is right at the designing phase, it will bring out this particular square region and tell you that, hey architect, hey designer, this is not receiving the enough amount of sunlight that you desired to. Now it's your choice to move forward or to change that. So maybe as an architect, you could plan some activity that is not very active during the day, right? So this is how you make informed decisions. So the biggest outcome is informed decisions. You are not just randomly guessing and making some designs. You actually have the data to back that design. Okay, that brings us towards the last slide of this presentation, and then we move on to some practical aspects to see how what Grasshopper and Rhino has to offer. So let's talk about why does architecture need computational design? Why do we need it? So there is something called multiple design iteration. So what I could do is I could tell the computer, I'm just oversimplifying everything here. So let's say this cuboidal elevation is the building. So I could tell the computer to start trimming out this particular side at an angle until it reaches 60% efficiency in terms of solar radiation. So what computer would do is start making different iterations of this design, right? And it would say this is 10%, this is let's say 20%, and this is 45%, this is 60%, and this is 80%, right? So it will give us multiple design operations based on our parameters. Second thing is repetitive task automation. So if I go to the let's say this slide here, so imagine if this is a building. So imagine if this is a building and these are some openings in the buildings. So and this building has 5,000 windows. Okay, you buildings don't have that many windows, but let's say it has 5,000 windows and there is something called door window schedule, right? I'm sure most of you must have heard about it. Door window schedule. So what is door window schedule? It is a technical working drawing in which you tell the fabricator the exact dimensions and specification of a window or a door. So if this is a window, you will have to give out the dimensions of these what is the trim size, what is the radius, what is the material being used, thickness, and all these things. Now imagine if you had to make 5,000 windows yourself manually on AutoCAD. It would take you months, right? And to make all these dimensions. And then again, if there was some change in the design, you would just quit the job. You would not go forward with the job. So this changes with parametric architecture. You can automate this process. So you can tell the computer to extract all these openings, orient them in an XY plane, and then kind of make a label all these dimensions, and you can directly export AutoCAD drawings with one click of a button. So you can this task does not require any brain. This task does not require brain. It is sheer labor. It is a tedious task. It just requires labor. So why go through the extra labor? Why not use our head into something creative and let the computer do the labor? Okay. So repetitive task automation, and finally testing the design. So I have talked very much about this. So let's say if there's a building, you can test it on various parameters like the sun or the wind. You can also simulate seismic activities and see how it is performing. You can simulate loads and see where the beams are deflecting or where the structure fails. So you can perform various different simulations, or you could test the structure before even designing, and all of these things right at the conceptual stage. No need to wait for the entire process to complete and then towards that, towards fabrication, towards testing, and realize that your building is not performing very nicely. You do it right at the conceptual stage. Okay. So that brings us towards the end of the presentation. So I'm just gonna open up Rhino here, and let's have a look at Rhino. And great. So I see people, most of you are architectural students, some of you are architectural graduate. That's great. Okay, so let me go ahead and launch Rhino. Let's see what's causing Rhino to hang. Okay. I'm just gonna stop the screen share for just a moment here. So I wonder why Rhino just started crashing on my system. Let me see if I can quickly fix it. Okay, guys, I'm just connecting right back in. I believe my Rhino is crashing, so let me go ahead and just restart the system. And it would be a minute before I join back in, so hang on, right? Meanwhile, maybe you guys could start interacting with each other and see where you guys are from, and let's have. And also, I would like you guys to drop in your email address in the chat box so we could also share the scripts that we do dive in today with. Okay, I'll just. Okay, seems like we are back online. So let me also just resume the Google Meet chat. Okay, I apologize for the delay, and yes, seems like we are back online. So seems like we are back online. So I'm just gonna share the screen again. Okay, so let's begin by understanding what is Rhino, why it is useful, and why should we prefer it? Why should we prefer using it? Uh, what is Grasshopper and what is the difference between other modeling tools and other 3D tools and this particular tool here. So let me bring up a whiteboard quickly. So I'm assuming that most of you are beginners, so I'll just cover a quick couple of basics of what 3D modeling is. So I'm sure most of you must be aware of what is a point. It is a dimensionless unit. Then if you combine 2 points, you get a line. It's 1D. Basically, it has length and a direction, right? And then if you combine these lines so that they form a closed structure, so this is a shape basically. And this is something very basic that you guys have covered, must have studied in the first year. So this is 2D, and then if you combine them, you get a 3D structure, something that is 3D. So this will have area and this will have volume. Okay. So these four blocks that you see, basically Rhino looks a bit complicated at first. It looks a bit intimidating, but it is very easy because you can clearly see that we have curve here, right? And there are some options, and then you can also find the same options here. So basically everything is repeated multiple times. Same options are here, same commands are here, the same commands are here, and same commands are here basically. So that is why it looks a bit intimidating. So we'll stay in the standard bar right now. And these are called viewports where we visualize our geometry. So this is top, perspective, right, and front. If you double click on any of the names, it maximizes. Okay. And then you could drop, if you go to this particular point icon here. If you click on this arrow, you'll see multiple point options. So we'll use the first and the second one. So if you just type in point, hit enter, you can place some points on the viewport. Okay. Down here is the snap setting through which you could adjust snap just like CAD programs. So end, near, point, and all these things, and you could disable them altogether. And then here down here you see some other settings, and what I'd recommend is to keep this gumball on. Gumball is an important plugin. Sorry, is an important tool. So what gumball is, if you select something, if I turn this gumball off, you see the gizmo on the screen disappeared. If I turn it back on, so whatever you will select, it will give this gizmo. So this is basically x, y, and z direction. This is z direction, this is x direction, this is y direction. Okay, so you could drag, click, and drag on these arrows to move subgeometry. You could also extrude them, you could also rotate it. So let's try all that out. The second one here, and the third one here is polyline. So just like PL entered in AutoCAD, this is a polyline through which you could construct or make a set of straight lines that are joined in together. You could also type polyline for that. And then there is something called inter CRV or interpolating curve. Inter CRV. So what inter CRV does is it allows us to make some curves. So let me just make a curve here. So now you see the fun part about this curve is whatever points I'm clicking, the curve is always passing through those points, right? And the second type of curve is NURBS curve, or instead of NURBS curve, you could just type in curve. So what this particular curve does is, if you'll draw something, the curve will not pass through those points. Instead, it will be controlled through those points. So I hope you guys get the difference between a NURBS curve and a NURBS curve and an interpolating curve. So interpolating curve basically passes through the points that you make, and NURBS curve doesn't. It is controlled through those points. Let's go ahead and explore a couple of more things before we move into the fancy technical stuff. Let's just have a look at all these things. So I would actually recommend you guys, so once you are actually practicing after this session, go ahead and explore these options. These are some options to make circles and polygons and sort of these sphere ellipses and arches, rectangles and triangles. So the first one here is if I click on this one here, you see I can make some 3D geometry, and we can change how this 3D geometry is looking by clicking on this arrow here, and we can change the style of preview. So we can either set it to wireframe or shaded or rendered or ghosted. So for now, I'm just gonna set it to shaded. So if I talk about this particular geometry here, I can go in here and make some cylinders and make some different shapes. So let me make this. So I made a cuboid along with a sphere. So then there is some command here through which you could, right now this is a different geometry. This sphere is a different geometry, and this cuboid is a different geometry. What if I wanted to combine them together? What if I wanted to uh, probably subtract this sphere from this cuboid? So to do that, there is this Boolean different option that I would actually want you guys to explore these. This is not parametric, this is some basic modeling tool. So Rhino is a 3D modeling tool just like SketchUp or any other 3D modeling tool, but it is a bit more sophisticated. You have a bit more control over the geometries that you're making. So that is the difference between Rhino and any other 3D modeling tool. So I would encourage you guys to actually explore these tools. So let's say if I type in Boolean difference and I select this cuboid and hit spacebar or enter and then select this sphere and then hit spacebar, you see it has kind of removed that spherical surface from this cuboid. If I press Ctrl Z, it will just undo it. And I can combine them, I can do a Boolean intersection. So I would actually encourage you guys to try these out once this session is over. Let us see a couple of interesting things first. So you can select every geometry, all the geometry, move it aside, and after selecting it, you can also hide it. So in order to hide it, you can click on this light bulb option here. So you can hide it from here, and if you right click on it or click this one, it brings everything back on. So I'll just hide everything so that it does not interfere what we are making right now. So let me go ahead and make a couple of curves. So this is a curve that I just made, and I'll make a copy of this by pressing and holding Alt and moving this particular curve. So I have these two curves. What if I wanted to make a surface between these two curves? So let's go back to the drawing board again. I'm trying to break down the complexity of what curves are and how they perform and what is a 3D geometry basically. So imagine a surface like a piece of fabric. So either you throw it like a t-shirt. So how does the fabric look? It has threads that are weaved in both directions, right? Correct? So similarly, and no matter whether you wear it or whether you throw it on the couch, whatever you do it, it will take that shape. So similarly in 3D tools, particularly in Rhino, these threads are called, this horizontal one is called U and the vertical one is called V. So this is very important, U and V. So what if we had to make a surface between two curves? So what we could do is, so if this is a curve and this is a second curve and we want to make a surface between them, so what computer does is it breaks down this curve into parts and it will start numbering them. So computer always starts numbering from 0, so it will say 0 1 2 3 4 5 and 6, and similarly here it will break this curve into multiple parts and it will label it 0 1 2 3 4 5 and 6, and then what it will do is connect 0 with 0. Then it will connect 1 with 1, 2 with 2, and so on and so forth. Okay, and there it has its v values. Now what it will do is it will subdivide these vertical ones. So for the sake of it, I'm just doing 4 divisions and I'm not gonna draw in each one of them. Okay, let me quickly do that. So it will divide something like this and it will make this 0, this will 1, this will become 2, and this will become 3. And then it will start joining all the zeros together, all the ones together, 2 together, and then finally 3 together. So this will be U. And that is how it makes a surface. So let's try to do that on Rhino. So what if we wanted to make a surface between these two curves? So there's a command called loft. If I type in loft, it asks me up here on the top, select curves to loft. So I'll select this curve and I'll select this curve. And if I press spacebar, you see it has kind of made divisions and join these curves together. So I'll say do not simplify and hit OK. So you see very easily I made a very curvilinear sort of surface. Let me go ahead and quickly make one more curve and let's try to make something interesting out of this time. So imagine if this is a curve and let me make a copy of it and I'll change how this curve is in its form. So let me change it a bit. Okay, let's make a lofted surface between these two curves. So I'll type in loft, hit enter. I'll select this curve and press spacebar, and there you have it. So you see, you can make very organic and smooth shapes, fluidic shapes, very easily in Rhino. But the only problem is, if I go back and select this curve, and if I change the shape of this curve again, the surface won't automatically update, because this surface is a different unit and these curves are a different unit. So I'll have to do the loft again. And this is what changes with parametric architecture or with computational design. So enter Grasshopper. Let me go ahead and quickly launch Grasshopper. Okay. So this is Grasshopper. Let me introduce you guys quickly what Grasshopper is. So this rectangular boundary that you're seeing here, let me increase this pen size. This is called canvas. So you draw or you make everything in here. So Grasshopper is a visual scripting software. It's a visual scripting plugin that is very tightly incorporated with Rhino. So whatever you make here on Grasshopper, it is previewed in Rhino. Okay, whatever you do here, it is previewed in Rhino. So these where my cursor is right now, these are called components, and you might not see this many components on your screen because I have many plugins installed. That's why I have these many plugins components. So these are called components, and let me go ahead and drop in a component here. So you can double click anywhere and type a name of the component, say point or a line or anything, and or you could drop it from here. So if I double click and type in point, it will bring up the same thing. Okay. Now let's understand what this is. This is known as a component. I'll write C for it. Component. This here is input node. This is an input node. And this here is output node. Okay. So we always connect output of one component to the input of another component. And it will all make sense in just a bit. So I'll just keep it somewhere here. I'll keep it aside and I'll just also move this geometry aside and hide it. So what can we do in Rhino? What can we do in Rhino and Grasshopper combined? So if I make a couple of points in Rhino itself, so let's say these are 4 points that I just made in Rhino itself. And now there is something that means with the color of the component. If the component is orange, that means the component is empty. And you can click on this balloon here to see what is the error. So it says floating point parameter point failed to collect data, because we did not specify any point in this particular component. That's why it's orange right now. So all these black icons that you see here, all these black icons, they are used to reference something from Grasshopper, Rhino. So let's bring these points here in Grasshopper. So I'll right click and I'll say set one point. And as soon as I click on set one point, Grasshopper screen disappears. Now I can select a point here, and as soon as I do that, it will bring up the Grasshopper screen back again. Okay. So this is a point. Now you see there is a green mark because this component is now naturally white in color. That means it's running fine. It has some data in it. It is running fine. And if I select it, you see this point here turns green. And I can move this point in Rhino, and it will automatically update the position of Grasshopper's point. Okay. So let's see what we can do out of it. So there is something called panel. So panel is used to check the output of these components. What is it giving? Because we cannot see any geometry preview here, right? We can only see it in Rhino. So let's see what it has in it. If I drag a wire out of it, so you just click and drag, a wire comes out. So if you connect it like this, it says 0 referenced point. 0 referenced point. Why? Because we referenced one point from Rhino. Let's quickly reference another point and make a line between them. So I'll again type in point, right click, set one point. I'll select another point. I'll select this one. Okay. Let's also check the output of this one. It also says referenced point. So this one is the green one here, and this one is the green one there. So let's make a line. So if I double click and type in line, I won't use this black one because black components are used to reference something from Rhino. I'll just use this line here. So let me go ahead, and now you see what does a line require. Okay, what does a line require? It requires a starting point and it requires an ending point, right? So I want to make this point as the start point, so I'll just drag an output and connect it here. And I'll drag an output from here and connect it here. And as soon as I do that, you see a line is being made, right? A line on Rhino, I can see a line on Rhino. And again, if I move this point in Rhino, the line also automatically updates based on the position of these points. Correct? Let's check the output. So if I connect this line here in the panel, you see it tells me that it is a line that has a length of 196 units or 196 mm. Why mm? Because you see down here on Rhino, the unit is set to millimeters right now. Okay, so this is a line. I made a line. That's cool. Let's try to make some curves. So I'll just type in point. And now again, it would be very tedious and very boring if you had to select all the points manually one by one. So what you can do is you can right click and select set multiple points. So as soon as you do that, you can select multiple points in one component itself. So you see I selected these 2 points, and when I hit space bar, both of these 2 points automatically get highlighted in green as soon as I select this component here. Okay. So this one here has the first point, this one here has the second point, and this one here has the remaining 2 points. So let's try making a curve between them. Let's try to do that. So in order to do that, let's make a curve. Let me type interpolate. So as soon as I type interpolate, you see I get this curve. If you hover over it, let me just hover over it, and it says create an interpolated curve through a set of points. So now we have some points, right? We have like 4 points with us. So how about making a curve between them? So let's do that. So what we'll do is I'll connect this first point in the vertex here, and as soon as I do that, this turns red. Red means there is some error, there is something wrong with the component or something wrong with the input. So if I click on this balloon, it says insufficient interpolation points for a curve. That means we only gave it one single point right now. That's why it turned red. It cannot make a curve between one single point, right? It needs at least 2 points to make a line curve. So let's connect this second point as well. I'll turn the preview of this line off by middle clicking on it and choosing this blindfold guy. So let's give it a second point. But you see, as I try connecting the second one, the first one automatically goes away. If I connect this first one back, the second one goes away. So to connect multiple outputs into one single input, to connect multiple outputs into one single input, you press and hold shift. Okay. So if I press and hold shift, as soon as I do that, you see a plus sign appears on my cursor. And now if I drag and connect this wire in this vertices, both of them get connected. And let me also drag and drop this one. So now you see I have a curve that is passing through all these points. And if I check the output, it says planar curve because that's what we made. So let's try out another type of curve that's called NURBS curve. And let's connect this one here and press and hold shift, connect this one, press and hold shift and connect this one. So can anybody tell me in the chat box, we use the same set of points to make the curves, but why are these curves different in shape? Can somebody tell me in the chat box quickly, what is the difference? Why do we not have identical curves when we are using the same identical points? Anyone in the chat box? Let me have a look at the chat box. No one? Yeah, exactly. Very nice. So the first one is interpolating curve. So it will always pass through the points whether when and the second one is a NURBS curve. It will be controlled through those points. Okay. Let's try making a surface between them because we learned to make a surface between two curves. So let's try doing that in Grasshopper. So if I double click and type in loft, it is asking me for curves. So I want to make a surface between this curve, the one that you see in green right now, and this one. So let's connect this curve in here, press and hold shift and connect this curve. And as soon as I do that, you see I have a surface. And now when I'm changing the location of the points, the curve is getting updated. At the same time, the surface is also getting updated. And if I check the output, it will say an untrimmed surface. So that is the power of computation design. You never lose control. So just like layers in Photoshop, if you work in layers, the data is not destructed. Similarly, in a way, we work on Grasshopper. So let's try to make something more advanced in it. So let me go ahead and make a curve in Rhino itself. So say this is a curve. I'll make a copy of it and I'll probably alter the shape a bit. Okay. And I'll make a second copy of this as well. So let's make a lofted surface between three curves this time instead of two. Okay. So let's try making a surface between these three curves. So in order to bring these curves in Grasshopper, I'll double click and type in curve. And again, this black guy appears. I can use this to reference curves from Rhino. So I'll right click and say set one curve and I'll select this curve. So you see that this particular curve is selected. And what I can do is I can press Control C and Control V to make a copy of this same component. And in this one, I'll say set one curve and select this middle one. And in this one, I'll say set one curve and select this one. I could also have done set multiple curves and selected all of them at once. But for the sake of this example, I'm using these three different ones. So if I double click and type in loft, and if I connect this and press and hold shift and connect this and this, you see I have a very smooth fluidic shape. Let me change the preview style a bit. Fluidic shape in here. And now if I select these curves and change the curve, the surface automatically updates. So no matter how many times I change something, it will automatically update because I made an algorithm like that, right? I could even change the position of this entire curve. Okay, let's move forward. Let's see what else can we do in here. So if I check the output here, you see it says an untrimmed surface, right? What can we do out of it? How about, say, we have, let's say we have a surface like this. How about dividing it into panels and then doing something on each of these panels? How about that? Let's try doing that. So let's divide this panel, this particular face or surface. So in order to do that, what I'll do is I'll double click and type in surface here. I'm just trying to sort the script. It's a left to right approach. So you see, uh, it can get messy pretty quickly if you do not keep on organizing it very nicely. So because there are so many wires that come from here and there. So keep on organizing your scripts. So I'll connect this loft in this black guy here. So now I have this surface here. Let's divide it. So in order to divide, there's a component called Isotrim. So what Isotrim does is it requires a surface that it can divide. So I'll connect this surface here. And then it requires the information of how to divide it. How many divisions, how far from one another, and basically how to divide it. So if I double click and type in divide domain square, there's another component called divide domain square. So this gets connected in domain and this surface gets connected here. And in this u and v count, we can provide the number of divisions. So let me say 15 by, sorry. Okay, double click, type in any number, it will bring up a number slider. So I'll connect this 15 here and I'll connect this 15 here. And if I zoom in, you see if I change this number, I can adjust the number of divisions on this surface. So let me say 15 by 11. Again, if you can see, there is u count here and there is v count here, as we learned before. And also, this is a kind of a thumb rule. Isotrim and divide domain square, they usually go in together, always. Okay. Now, if I check the output from here, it was one single surface, right? This entire surface was one single surface. Now, if I check the output from here, from this isotrim, you see I have 165 surfaces. Why 165 surfaces? Because the counting starts from 0 in computer. So 165 surfaces. Why? Because 15 into 11 is 165. So now it is no more one single surface. It is rather 165 individual surfaces. So we just divided this surface. Okay. Let's move forward and let's see what else can we do here. Right now, we do not know what is the center point. Let's say if I draw, let me change the ink color. Let me draw this one, a blow up of this one. Let's name it, let's say 21. So this is 21. So we don't know what is the size of this, right? We also don't know where is the center point, and we also don't know what is the normal direction. So normal direction is basically the perpendicular direction. So the 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 geometry could be oriented in any way, right? The entire panel could be oriented in any way. So we do not know what is the normal direction as well. So let's in order to get that information, there's a component called evaluate surface. Let's go back and use this component. So if I double click and type in evaluate surface, and now you see it is asking me for a surface and it is asking me for a point. So I'll connect this surface here, and there is something called MD slider. I'll connect this MD slider in this point. And what I'll also do is right click on this surface and click on reparameterize, and I'll explain what reparameterize means in just a bit. So always remember that MD slider and evaluate point go together, and you always reparameterize it. Always. This is a thumb rule. You always reparameterize it. So now let's understand what is reparameterizing. So reparameterizing is basically nothing. Imagine if you had a rope. So this is rope, and it's the length of this rope starts from 0 and it goes up till 20 units. Okay, so somewhere here in the center must be 10, somewhere here must be 5, and somewhere here must be 15. So now if I reparameterize this surface, so if I reparameterize this, what it will do is it will take this entire rope. Let's call it a rope. Let's say it is a rope. It will take the same length of the rope. It won't change the length of it. It will only change these numbers for us to make it easier. So it will change this 0 to 0, and it will change this 20 to 1. The length will remain the same, right? It will only change the name. So this will become 0 and this will become 1 unit. And somewhere here in the center will be 0.5. Here would be 0.25, and here would be 0.75. So this is what reparameterize does. So in case of our panel, so this is how our panel looked, right? So earlier this point must be 0 comma 0. This must be x comma 0. This must be 0 comma y, and this must be x comma y. So basic graph system. When I reparameterize it, so I'll choose yellowing, and if I reparameterize it, what it will do is it will keep this 0 0 as 0 0. It will change this x comma 0 to 1 comma 0, and here it will change it to 0 comma 1, and here it will change it to 1 comma 1. So now if I have a graph that starts from 0 and goes up till 1 comma 1, I can go anywhere on this surface, right? Irrespective of the length or the breadth of the surface. So that is what we are doing through evaluate surface. So when I reparameterize it and connect an MD slider, you see this MD slider goes from 0 to 1 comma 1, and based on the location of, so let's talk about this panel here. If I bring it here, you see the point comes right at the center starting point, and then I can adjust where it goes through this particular graph, right? So this is what reparameterize it. Let's move forward, and let's make some circles on this particular surface here. So in order to make some circles, what we can do is if I double click and type circle, and again this black one would be used to reference something from Rhino, this would be used to make something in Grasshopper. So I'll use this one. So now it is asking us for a plane and for a radius. So if I connect, so what does a circle need? If we have to draw a circle, what does it need? It needs a center point, and it needs a radius, right? So that is what it is asking us, a center point and a radius. So evaluate surface is giving us points, the center points, and the position of these center points can be controlled through this MD slider here. And if I actually go ahead and check the output from this point, you'll see these are coordinates basically. So points have coordinates, right? X, Y, Z coordinates. So that is what these coordinates are. So now irrespective of length and breadth, we can make some points on these surfaces without caring about how big the surface is, how it is oriented in the 3D space, how it is performing in the 3D space. We can just directly use evaluate surface. It makes our lives easier. I'll change the number of divisions a bit. Okay, this looks fine for now. Okay, so if I connect this point here, and let's say if I double click and type in 15 and connect this radius here, so probably 15 is a very small number. Okay, so now you see it has made circles at each of these points, right? It has reduced our labor, and it has kind of made these points at each of these center points. What can we do further? What can be done further? So right now all of these circles are kind of intersecting this surface. They are not on the surface, rather they are intersecting it. So how do we change that? So I'll just select it and probably turn the preview of it off. There's something called circle CNR. So what circle CNR means is it requires a center, it requires a normal direction, and it requires a radius. So we already know what center is, we already know what radius is. Normal is basically the direction. So you see evaluate surface here is giving us the normal direction. So we can connect this normal here directly. So if I connect this point in center, if I connect this normal here, and let me connect 50 in the radius, let's see how that looks. Okay, that's a bit much, so I'll reduce it. So now you see that I have very easily drawn circles that that are right on this surface, laying flat. And again, if I wanted to extrude them, I could just simply use a command called extrude, and I can connect this circle in base here, and in direction I could give it a direction. So I'll just use the normal direction. So normal direction is basically 90-degree from this surface. Normal, basically 90-degree from this surface. So I'm getting a normal output from this evaluate surface. I'll use this only. So there is something called amplitude. If I use amplitude and connect this normal in vector here, and let's say if I connect a unit of 20 and connect this vector in direction, I can very easily extrude these circles into kind of cylinders. Let me change the preview style, and I'll kind of give a quick recap here. I know uh, in the beginning it is a bit complex to grab on to Grasshopper, but once you get the algorithm, it's fairly simple. So this normal is basically giving me the direction of the normal. What is the direction of the normal at this particular surface here? But and this amplitude is controlling the length of that normal, how far it should extrude. So you see I can control the length from here, and this is extrusion. So the fun thing is if I change the preview style here, and if I turn all the geometries back on, and if I go back in Rhino and let me change the shape of this curve. So you see, I'm going back, right back at the first stage, and as soon as I change the surfaces, the shape of the curve, everything automatically updates, from cylinders to the shape of the surface, everything automatically updates. So let me, you see how easily I can control it, and I can always go back and also change the number of divisions. So if I change the number of divisions, you can see that how the number of circles automatically increase, right? So this is the power of computation. You never lose data. You can always go back, change anything. I can move move this MD slider to change the position of the center point, and I can move these cylinders here and there. Or I could go back to circle and increase its radius. I could change how this particular number slider operates. So let me give it 150. So if I plug 150 here, you see I can change how far they are getting extruded, right? So this gives us an extraordinary power. Now imagine this was a facade. I'm not, I mean, this is very early to move to facades. But imagine if this was a facade and you had to design some openings on it, circular openings on it, you could do that through this. Let's make it into a cone. So in order to make it into a cone, I'll double click and type in cone. So if I type cone, I'll turn the preview of this extrusion off. So it is asking us for a base, it is asking us for radius and a length. So if I connect this circle in base and I connect this radius 47 in radius here, and in length let me say 150, and if I connect here, you see I have cones on each of these panels. So it's, and you can clearly see that the computer is not automatically making it us for us. In a sense it is, but we are telling it how it has to make whatever it has to make. It is not automatically doing anything. So that's something that was a myth, kind of a myth, that people think that parametric architecture will give you the design solutions automatically. Okay, so we have the surface here. What else can we do? We have these cones. What else can we do? So let me go back to Rhino, and there is this called surface. If I hover over it, it says surface from 3 or 4 points. So I'll choose, uh, let's say this one, surface from 2 points, rectangular plane, corner to corner. I'll make a plane. Okay. If I select this plane, I'll minimize grasshopper. So if I select this plane and type in rebuild, I get this dialog box in which I can control how many U and V divisions should be made. So let's say 8 by 8. And if I hit OK, and for Rhino 6 users, you press F10. For Rhino 5 users, you type in points on. So you see it brings all the division points. And now I can select these points and move them up and down. So very easily I can make some very organic shapes, very fluid organic shapes. So, so you see I made this very organic shape very quickly in Rhino. It would take ages to make something like this in SketchUp. So let me bring Grasshopper back. And now we have made a working algorithm to to divide a surface into panels and to make cones on it, or to make circular extrusions on it. What if we wanted to do the same on this surface? So it's very simple. What you can do is double click, type surface, right click, set one surface, select this surface. I'll hide everything in Rhino. And there you have a surface referenced in Grasshopper. And we could directly just plug this surface here. and the entire algorithm would automatically be repeated, and we'll have these divisions on this particular surface here. So you see, if you develop algorithm for one building, you could apply the same algorithms to multiple buildings, or if you develop something for a small little facade of a building, you could apply that to to multiple, and then again you could go ahead and tweak it to change how it looks to suit your needs. So that is basically the power of computation, and that is why it is very much needed right now. Right, any doubts so far? If you guys have any doubts, you guys can unmute yourself. Let's have a quick Q&A for 2 3 minutes, 3 4 minutes, and then let's move towards the last segment of this session. And guys on YouTube, you can start posting your doubts in the chat box. So let me go back to, yep,
Hello.
yep.
Yeah, so can we move the surface by moving points in the curve just in Rhino without grasshopper? Like without entering into all these complicated grasshopper stuff, can we make a surface and then just alter the surface with the curves point?
uh, so you could make changes in Rhino, but then again, since we made an algorithm in Grasshopper, everything won't be replicated automatically in Grasshopper. Sorry, it won't update the entire surface or the curve and everything that automatically updated. It won't do that. You'll just have to press Control Z to go back to the first stage or the first step, and then start from scratch, just like SketchUp. If you make something and you realize that I do not like the shape, what do? Either you start making it again, or you kind of uh, go press Control Z and go back and edit it again. So there are some plugins available for Rhino that sometimes do the job, but Grasshopper altogether offers us much more editability. And this is like, we have not even scratched the beginning of Grasshopper. This was just to give you guys an idea of uh, what what parametric architecture has to offer, and what all things could be done out of parametric architecture. Right? Any other doubts?
Thank you.
Sure. We have many people on YouTube, so if anyone has a doubt on YouTube, mobile de do. Okay, so I think not many doubts here. Let me have a look at the chat. What if we want to do some changes in the second surface that you just created, but not in the initial surface? So Krina Panchal has a question on YouTube, that what if, let me go ahead and share the screen. Okay. What if we wanted to make the changes in the first surface without altering the second? What if we want to make some changes in the second surface that we just made, but not in the initial surface? I'm not sure if I get the question, but I believe you're asking that lofted surface that we made here. So what we can do is we can just copy paste this entire script. We can just select it, Control C and Control V, and you could plug in any surface here. It would repeat all the things to that particular surface. Or if I go back in Rhino and if I select this surface, let me turn the preview of this one off. And if I type in points on or press F10, and I can still go back and edit these points. And you see all the cones and everything is automatically updating, right? I am making changes to the initial surface and everything is updating. Can the extrusion made here normal to subdivision be a function of the area of the same? Yeah, definitely. So instead of giving a length here, you could use area and use that area as amplitude. Shravan. Then Yogesh, a Rhino support BIM. Rhino does not directly support BIM, but in Grasshopper, you can directly, Grasshopper can be integrated to ArchiCAD or Revit. So you can do the entire BIM workflow through that. Okay, so let me go ahead and
Excuse me, sir.
yep.
I wanted to know how would we incorporate the climatic data or any other data with the grasshopper, because it is definitely giving us numbers, but how do we incorporate it with that data so that we know
So
where to?
sure, I get your question, Abhinav. So right now, what we have explored so far is is like just understanding the interface, how things are connected to each other, how you start making some geometries on Rhino and Grasshopper. Parametric architecture in Grasshopper itself is a very elaborate thing, very elaborate thing. So there are plugins like Honeybee and Ladybug. I'll just talk about climatic analysis and all those sorts of analysis and how you can proceed further. So it is a complex task that requires some sort of learning, some sort of basic understanding of the tools first, in which you start to create geometries, you start to learn how lists and data structures are managed, and then you move on to climatic analysis. So we can perform all sort of climatic analysis, structural analysis on Grasshopper itself. Uh,
Thank you, sir.
sure. So let me go ahead and bring up the closing presentation through which we will explore how. Let me. Okay. All right. So let's talk about scope of parametricism. Right now we have just explored, we have just very slightly, and I cannot put more emphasis on it, we have extremely slightly touched upon what Grasshopper, what these tools have to offer. So by merely by understanding that, I'm sure you guys can break this down now. So you can see that there were some curves here that were lofted in together to make this surface, right? And these modules are basically 3D printed triangles that join in together. If I talk about this, so construction, I don't want to get into the details of construction. We all know how elaborately parametric architecture is being used in construction as well. Let's talk about furniture. So whatever we have learned, the very basics, you can see that if you make a cross section of this curve of this furniture here at this level, and maybe at this level, and if you lofted them all together, you'll get a bench like this, right? So all you have to do is make a couple of cross sections and then loft them together. Similarly, so furniture industry, interior designing, interior facades, ceilings, product design, everything that you see that is designed and exists in physicality can be replicated through parametric architecture or parametric approach. So this vehicle that you see here, so this has an algorithm that there is a point here, and every all these sort of everything that is closer to the point has greater white, and everything that is far away from it has greater blacks. Similarly, in fashion industry, if you search for Neil Peart, and there are, I mean, I'm just showing this slide for you guys to open up your horizons and see what is the scope. Search for parametric clothing. So this is called program deformations. Program deformations here. So fashion industry is kind of now booming with it, and footwear industry. Let me talk about footwear industry. So companies like Nike, Adidas, Reebok, they have been researching and producing shoes extensively, that are 3D printed and that are designed parametrically. And how? So imagine if this is a shoe sole, and forgive my drawing here. So when a person stands, he or she exerts the most amount of pressure in this region of the shoe sole. So why to have the entire load bearing material in the entire shoe sole? Why not just give it in this region? So as you can see, the meshes here are dense. Some at some points it is dense, and at some points it is relaxed. So what this offers us is light lightweight footwear, because you cut down the material and then you also reduce material cost. And these were earlier being made for athletes, now they are being mass produced for everyone. So that's how you have lightweight footwear that will support you perfectly, right? And then there is jewelry design. This particular jewelry has been designed using a plugin called pufferfish. So everything, all the products that you see can be inspired parametrically or computationally and can be designed like that, and then they would perform better. They would Parametricism is just not about complexity, it's all about optimization. So then there are some digital fabrication techniques, and I'm sure most of you must have heard and even used CNC laser cutting. So CNC laser cutting is a 2D technique in which you produce polylines and directly cut them on a piece of metal or boards, and then assemble them. And then there is something called CNC milling. It's a 3D process in which there is a drill bit involved that not only moves in X and Y direction but also moves in the Z direction. So you see it kind of makes these shapes. And then finally there is also something called robotic arm fabrication, but I'm not going to talk about it because it's not available in India. Robotic arm fabrication. So 3D printing. If we talk about this chair here, so if we talk about this chair here, uh, when a person sits on it, this is a 3D printed chair, and it's not a conceptual image, it's a real image actually. So if a person when a person sits like this, right, the most amount of pressure is exerted in this area. So these colors that you see here are not merely for aesthetical purposes. The darker the shade of blue, the higher the compressive and tensile strength of the material, and as soon as you move towards white, the strength reduces, so thereby reducing the cost of the material. So that's how this chair has been fabricated, and it wasn't fabricated in just one single piece. It had 5 different pieces. So this piece was made first, then this was made, then this was made, then this was made, and then the top piece was made, and then they were assembled in together. So that's how you evolve your processes. Let's move forward, and then there is something called waffle structure. So to talk about waffle structures, let me open up a Chrome window first. Then maybe I'll head to. Let me go to Instagram. Okay, so this structure that you see here is a waffle structure that we fabricated in one of the workshops. And how was it made? How is this particular structure made? So waffle structure is, let me bring the slideshow back again. So a waffle structure is made by so you see that this shape was basically designed on Rhino and Grasshopper, and then it was divided in X and Y directions. So this is X direction or U and V directions, right? Just like we how we used Isotrim, and then it was also divided in the other direction, and each of these curves were extracted, and then they were kind of there was They were laid flat on the ground, and there were some slits made in which two different objects can get attached. So that's how waffle structure works. So you can easily break down. It's all about creating complexity with simple things. So waffle structure is a very simple thing, but you see this structure, it looks very complicated, right? So it's all about creating complexion or complexity through simple surfaces or simple things, and that's how elegancy is created. So when you see buildings of Zaha Hadid and all these big architects, the complexity is basically created through these simple techniques with repetition of one single element, probably one single surface that is entirely enveloping the entire geometry. So that is how this waffle structure was made. And if I talk about this, this is a structure by the an association called the Very Many. I would encourage you guys to have a look at it over the internet. The Very Many. So this is a complex looking form, and it is made with aluminium sheets that have a thickness of less than zero point 0.1 millimeter. And how are these made? If I make some lines here, you see there are some lines like this, right? If I draw some lines here, so you see it is not one single surface, rather there are strips like these, correct? I hope you guys can see these strips. That's why I'm kind of tracing them through this red pen. So what are these sheets? These sheets can be unrolled. So if you look at the camera, for the people on YouTube, I'll bring this up. So if you look at the camera here, so this is a piece of paper, and if I can lay it flat on the ground, I could also rotate it, like if I could flip it like this, and now I have a pipe, right? And this pipe could get attached to the another pipe, and then another pipe, and all these papers could be of different dimensions. So let's see how that particular structure was made. So let me clean all these things. uh, okay. So if I talk about this first strip here, if you unroll it, it will look something like this. And these tongue that you see here are basically for riveting. So this tongue will be twisted and attached with this hole here through rivet joint. So it will make a pipe tubular structure, and these tongues will be attached to the adjacent strip that would be somewhere here. So there would be an adjacent strip, and it would be attached to those through rivet joints. And if I tell you this structure was fabricated by two people in 3 days, and we can unroll this and CNC cut this structure, right? We could very easily CNC cut this structure. So it's all about how you can realize very complex forms and then simplify the entire process. Okay, let's move forward. Uh, I'm sure you all must have seen complex walls, parametric furniture, parametric benches, elevations, and whatnot using modern materials. And we have been doing projects like that, but we don't want to showcase that because you already must have seen all these things. What what is a bit unusual that we evolved at Equim is m- fusion of parametric architecture with vernacular or sustainable. So an opportunity presented itself before us last year, and we had to design a resort in Noida. That resort had only one constraint. It was an agricultural site, and we were not allowed to do any concrete construction on it. So we could not use shell, concrete shells. That is the most obvious choice for parametric shells. And we could not use space frames because again it would require some sort of concreting. So we retired to bamboo. So we started thinking how we could use bamboo parametrically to create something interesting. So we started designing these forms. So you see, these designs were made in Rhino and Grasshopper, and these were tested against the wind pressure because Noida receives cyclonic winds during monsoons, and there is a lot of in summer the temperature reaches around 50 degrees Celsius. In winter, the temperature reaches around 2 to 3 degrees Celsius. So a lot of temperature change, and also it also has very heavy rains during monsoon. So we had to see that this structure pertains, this structure sustains itself. So we simulated wind pressure, sunlight, and towards this side is the stage, towards this side is a very grand fountain, and then we kind of made these structures, and the drawings were exported. These bamboos were sent out to fabricators to bend, and we received these bent structures. And you wouldn't believe that the construction began around 15th of February, and by the time Corona hit us, lockdown hit us, these structures were made, and these were made within 2 to 3 days. And obviously, there is a lot of roofing that needs to go on top of this. There is a lot of finishing that still has to be done, and the construction is kind of paused due to COVID situation. uh, but we were very glad to see that even the construction wasn't finished, but it withheld all the cyclonic wind and all the monsoon pressures that we had this year in Noida. So then there was some tree canopy here, alongside which we had to make this particular bamboo gazebo. So these will offer some sort of outdoor setting, a natural habitat. And then again, similarly, this particular structure was evolved. So you see, without disturbing the natural ecosystem there, without disturbing the natural setting, we kind of merged, we kind of fused everything in together. And with this project, with this particular project, I want to demonstrate, I wanted you guys to understand that it is an evolving field. It is completely up to you how you can innovate. What new design technologies can you fuse with parametric architecture to make something completely unique, that is entirely unique to you? And again, there is no typical detail of making bamboo structures, designed parametrically and install them. Then we had to design those details, and that is what you have to do as architects. Then only you'll do some original work for yourself. With that said, let's also have a look at what is the future of computation. What does the future holds for us? Because so far, whatever we have studied, whatever we have seen, if I talk about the timeline of architecture, parametric architecture came into play somewhere around 1995, and in 2000, somewhere around 2010, AI came into play, artificial intelligence. Now we are living in a world of AI and ML, artificial intelligence and machine learning in architecture. This was the era of parametricism. So when I say this was the era of parametricism, that means we already are at an advanced stage, not in India but globally. So what does the future of architecture holds? So clearly, as we saw that automobiles are becoming an organism of their own. We saw that refrigerators are getting smarter each day, our phones are getting smarter each day. Similarly, our buildings need to evolve. And how? So I have a video here from Patrick Schumacher's presentation, Patrick Schumacher of Zaha Hadid Architects. Let's have a view, let's have a look at this particular video. So you see this furniture here is kind of adopting and changing its shape in real time. So the furniture during when the day started looked something like this, that had some group seatings, and as the day passes, some of the seatings become tables, some of the seatings become the wall, the partition walls, some of the seatings becomes the conference tables and conference rooms automatically based on how these people are moving and interacting with it. So this is AI giving that control. And I'm not saying we are there yet, but we need to look forward to this. We need to start researching and developing these things, because big firms, big architects out there are doing it. We are not in India. That's why we are lagging behind. Let's see what else do we have. So there are these kind of modules of seats that attach with each other, that can rotate. Now, okay, so this is an interesting one, in which through AI these humans are coded. So if you have to design a floor plate for 5,000, 3,000 people, maybe a floor plate that will accommodate 3,000 office people, can you predict the movement of in all the 3,000 people? No. How will they respond in the lunch hours? How will they respond during the meetings? How will they interact with their bosses? You cannot um, predict that using your head, but you can use AI, and you can use the data available on social media to simulate that. Now you see, this person is moving in the space, and this is being simulated through AI. And you see, he sees this person on his left, and it says Ethan male con conversion and not friend. He's not a friend. And okay, let me play it again. So you see how he has to go to the conference hall basically, and he's seeing all these people, and he's in real time making decisions. And based on these decisions, we can decide how whether the structure, that whether the planning that we have done, is it optimized for the users or not. Here we have 120 agents, and the total number of available workspaces is 142. So we are trying to identify the hotspots where collisions happen, where the traffic movement is the most. So it gives us that idea. So let's have a look at this one here. So this person is moving towards the reception table, and we can see what type of furniture option, how will a person respond to a type of furniture that is available. So we can also simulate all those things here, and based on the surrounding and the design, how the people are interacting with it. So this one again is an interesting one. This is a large floor plate where six workers and two managers are sitting in this area, and five workers and one growing company is sitting in this area, and there is four worker and manager in this area, and there are multiple companies. It's basically like a co-working space. So multiple companies are sitting here. So now we cannot ever predict how each of them will respond with each other, but we can simulate it. So let's simulate it and see how it's happening. So from 9 a.m. to 10 a.m., when they are working, that's how they are sitting and they are kind of working. Now 10 a.m. to 11:30 a.m. is when they start reporting to their bosses. So see, these people are coming and how they will report to their bosses. How will they respond, how, with the context. And this is where current occupancy is 24 and a capacity of 24 80 is available. Now this is recess time or lunch time. You see a definite collision happening in the center, where different teams are kind of interacting with each other. So we cannot ever predict all these things using just our head. We have to take help of computer, right? We have to take the help of the computer. So let me just quickly end this presentation here. Uh, okay. I'll stop the screen share to discuss what else could be done. So you see, all of you those who have webcams, you can turn them on. So what happens is, architecture is an evolutionary phase in India. Since our education is not up to that mark, we have been keeping architects away from technology, and we are moving into an era where technology is the biggest thing. Technology is the biggest thing. We are moving towards a future where Elon Musk's startup Neuralink just last month did its first test of integrating a chip within the brain of a living being, and he did it with a pig. And towards the end of the year, or towards the mid of 2021, he'll start some human testing. And 5 years, 10 years down the line, we will become cyborgs. Right now we cannot live 1 minute away from our phones. We are already cyborgs. So there is no point of keeping technology away from the designers. Designers of all the fields are using this power, but us. So let's evolve with technology. Why not evolve with technology? So to kind of visualize it, to kind of bridge this gap, to make sure that we have a system where architects of India and students of architecture of India are getting the equal kind of right and equal education as people outside of the country. We Equim Education has actually come up with an initiative of a series of workshops. So if I quickly go ahead and share the screen, so see, let's see what minimal surfaces are, how Frey Auto devised a methodology, how Zaha Hadid architects evolved it further to get the structures that we have now. So if I move on to equimdesigns.com. So there is this workshop called AI Urbanize that's going to happen on 23rd, 24th, and 25th of October. And then there will be a virtual exhibition on 1st of November. And in this, we'll be dealing with geo-urban and environmental analysis. So if I put it in easy terms, basically all sort of climatic and environmental and solar study, comfort analysis, maximizing the views while minimizing solar radiation and exposure, then mapping human interaction with the buildings, how humans interact with the building. When you design something for a city, it does not sit like an alien in that city. And coming up with multi-objective evolutionary algorithms and simulating humans inside the building, something that we just saw from the Hadid's presentation. And then there would be a competition and a design virtual designs exhibition on 1st of November. So, and we have a very celebrated young architect from India who's currently practicing in Dubai. His thesis, when he was merely in fifth year, his thesis won Best Thesis Award from COA on parametric architecture. He received many felicitations from President of India, and he's an advisory member of IJMAR. He graduated from Bartlett, UCL London on machine learning and AI in architecture. So, and now currently he's practicing in Dubai. He also gave a design entry for Notre Dame Cathedral Notre Dame in Paris, alongside Zaha Hadid and big architects, and he was shortlisted. Many of his works are actually displayed in museums. So he'll be conducting the workshop, and these are some of the works of the previous workshops, the works that some of the participants of these workshops have accomplished, and some testimony. So I would actually encourage you guys to go and have a look. So this is like an intermediate level workshop, and if you guys are looking for a beginner level workshop, there is a series called Parametrized. That is a 5-day program basically. That will The next Parametrized series is from 19th of November till 22nd November, and in which we will be looking into kangaroo, weaver bird, and starting from the very basics of parametric architecture, looking into list and data management and attractor points and curves, and also differential geometry analysis, And working with grids, on second day we look into parametric facades, parametric elevations, and the biggest thing that will come out of this one is how to develop computational thinking, because once you do that, then computational design is easy for you. On day 3 we look into meshes and form finding techniques of Antony Gaudi. So Antony Gaudi, if I search Antony Gaudi here, so this was this architect was particularly the architect who kind of revolutionized the architectural practices, and he's like one of the forefathers of parametric architecture. So how did he design buildings? So all these buildings that you see that were designed by him, they were, let me search spring experiment. So he basically suspended these springs like this, and then kind of inverted these structures. So this is a spring system. So if I go back to the whiteboard here, so imagine this is a spring, and if you tie a load here, so this spring would look something like this. And the beauty of this spring is it is optimized in nature. It is structurally optimized. So the tensile force, when once you invert it like this, equals the compressive force. So these are self-optimized in nature. So that's how he designed these buildings. So we look into these Antony Gaudi's form finding techniques, and then there is something called minimal surface. So if I search Frey Auto, and let me also go ahead and search soap bubble. So what he did is he used soap bubbles to inspire his forms. So soap bubbles have a tendency to create a minimal surface. So minimal surface is a surface that whatever area it encloses, it tries to maintain a uniform cross section throughout, and it tries to reduce the surface area. So he used inspirations from this. So have a look at this particular geometry here, this particular image that I have just opened up. I'll go back. uh, I'll go back once more. Okay, have a look at this one. This was designed by Frey Auto using minimal surfaces. And again, have a look at this one. Okay, now let's move to and have a look at this one. Now let's move to Zaha Hadid architects, and let's see how they evolved it further. So if I search Beijing Airport, so you see it's all about taking inspiration from architects and evolving it further, evolving your own technique further. So if I open up this image, can you guys immediately draw a relation between this and this one? So Frey Auto mostly used tensile structures or concrete structures. Zahadid used space frames, changed the design language a bit. So they evolved it further. So for Frey Auto, he physically made soap bubbles. So that was a very tough task. He physically made these soap bubbles to make inspire his forms. But we are living in a computational era. Zaha Hadid has been living in a computational era. Zaha Hadid architects. So they simulated it on computers. So now uh, they do not have to rely on the strength of soap bubbles, because they the bubbles burst very easily, right? So now we can do all sort of crazy things and come up with very creative forms. So that's what this workshop will be looking into on day 4 on minimal surface development. And then there would again be a lecture on digital fabrication and some case studies on parametric projects in India. And then again there would be a week of gap in which students will be preparing for the competition, and there would be a virtual exhibition. And let me go ahead and quickly show you the results of the recent workshops that we have done, how students have evolved through these particular. So all the images that you see on the screen are the works of students uh, that accomplished it in the 5 days of the course. So you guys can actually explore these things. We are sharing links on chat boxes, so you guys can explore these. So we had these competition entries, so if you have a look at these structures, so that's how they were, uh, the students kind of evolved these forms. They had to design a school in this one. So let me go back. So this entry came first. We had Vanna Sehgal, the architect Dr. Vanna Sehgal to judge the competition, and architect Amit Gupta of Studio Symbiosis, one of the pioneers of parametric architecture in India, who gave a guest lecture in the previous workshops. And again, if I go to the latest one that we just had, so these are some results that the students have generated so far, and we are very proud to present these works because they learn a lot from these workshops, and this will change how the new generation of architects design the structures in India. So have a look at the complex structures that they were able to realize in the course of 5 days. So that is what our approach should be towards designing. That we have to evolve, we have to learn. And right now, standard registrations for AI urbanized is live, and standard registrations is around 8,999 plus taxes. But for today, right after this session, for the next 24 hours, we are surging down the slamming down the prices. So if you register within the next 24 hours for AI Urbanized, that will be a very intuitive workshop that will change how you design and how you can justify a design entirely. So you can register for the early bird pricing within the next 24 hours if you wish to. So that would be 5,999 plus taxes. So right after this meeting, this close button will actually say open. And through this, you can go ahead and register yourself. And if you go to parameterized, early bird registrations for parameterized workshop, that is a beginner level workshop, are live. So you guys can go and check it out. And if you want, you can register it from the website here itself. If someone needs some additional information about the workshop, needs some help, you can drop us an email or go to contact and contact us. Some of the associates from our team, some education counselor will give you a call and talk to you. So with that said, I'll bring this webinar towards an end, and I just want you guys to understand. Let me also share a link. Equim designs.com/archive. I would encourage you guys to go and have a look at the works of students of first year, second year, third year, and even the architects that have graduated 5 years ago or last year have done. And you need to understand, we in India are currently lagging. It's your responsibility to make sure that the designer in you is getting the necessary education, is evolving, be it from any source, anyhow, because we we as the race are slipping away towards a very doomed future, and it's completely up to us how we can improve it. So let's take, would we get the recording of this session? This would be available on YouTube, Aishwarya. And guys, those who have not dropped their email addresses in the chat box, please drop them so that we can share the scripts from today. And that script will also contain some additional components as well that you can explore. And yeah, it was great catching up with you. And make sure you make a vow to yourself, a promise to yourself that you will do justice to the profession of architects, because we have a great responsibility. We have a great duty towards the society. What we build directly is responsible for how humans interact with each other. If the structure is heavy, the people inside it will feel heavy, right? So we are directly responsible for regulating the moods, for regulating the interactions, and above everything, When humans were hunters and gatherers, the homes that they lived in were made out of rocks. The rock homes represented the state of the human beings back then. Right now, we are in the phase where we have smart homes, smart watches, smart cars. Everything is smart. So our architecture is lacking behind. Fordism and post-Fordism, our architecture is lacking behind. It does not reflect the current advancement of human beings in the buildings. Merely putting 10 different sensors will not merely putting 10 different sensors and calling your building a smart building will not do any justice. It was a smart building 10 years ago, not now. It is dumb to just put some sensors and call it smart. We have to make the building come to life in a way where it has some sensors, where it can monitor the users, where it can accommodate and change based on the users, right? So all the best to you guys, and go ahead and check out the links, and in the chat that have been dropped in the chat box, recordings will be available on YouTube, and I hope to see you in the future session. All right, everyone. Bye. I hope you learned something new today.